But anyway, test crosses. If you don't know if a dominant-looking animal is homozygous or heterozygous, you can figure it out. You can test that by breeding it to a homozygous recessive. Good? Test cross. Yes, test crosses are on the test. But you probably knew that. Why did you know that? Because it's red. Very good. All right. We did our 93 to 3 to 1 magic ratio. We're in the middle of that. But in a 9 to 3 to 3 to 1, you've got 2 genes involved. Each gene by itself is 3 to 1, which tells you that each gene by itself is completely dominant. The 2 genes move independently of each other, and both parents are heterozygous for both traits. Do we agree? Now, we saw one where that wasn't the case. The ratio came out 1/4 to 1/4 to 1/4 to 1/4. That's why, but we knew because there were 4 phenotypes, we still knew there were 2 genes involved, right? Now we'll talk about blood type. You can put your head down. I know. We're going to talk about blood type. So, there are 3 alleles for the gene for blood, for ABO blood type. There's 16 for RH. You know, the RH positive or the negative thing. And basically, we just, if someone has any of them, we say, oh, they're positive. So, if they have any of the comments. But let's go. Is there everybody's fine if I erase this? Okay. So here's the deal. We have 3 different alleles, and where's my black marker? The black marker escaped. Ha! The black marker. All right. I'm going to write this. Do you remember I said that you need, if they're the same gene, to use the same letter? Right? Is A the same letter as B? How are we going to do this? Because I already told you it's the same gene, it's just different alleles. I don't know why, but some clever person decided that I is the letter that we will use. It's the way. Erica, you've seen it before, and not just me. You know this is the way they write it. All right, so what are we going to use for the dominant? Would it be the capital or the lowercase? Capital. So I said you have 3 alleles. 2 of them are dominant, and 1 is recessive. We're going to call this one IA. That's the one that causes you to make the A protein. It's dominant to this one, right? This one here is going to cause you to make the B protein. That's dominant to this one. This one down here, the O is, oh, we didn't put a protein on the surface. That's what it means. Literal, okay? So, let's just write down some genotypes and phenotypes, okay? Let's say we have a genotype. Let's do it this way, a little bit backwards. We'll have a phenotype of type A. There are 2 different ways you can get type A. Do you agree that you could be homozygous for A? Yeah, that's obvious. So you could be like that, right? There's another way to be type A. You can also do that because the dominant will block the recessive, right? What that means is this one says, don't think you need proteins and put them on the surface. There are no proteins. And A says, we're going to put A's on the surface. Screw that. So you got 2 different ways to make type A. You could be homozygous dominant for A. You could be heterozygous for A and still have an A. Do you agree? Now, Harris, tell me, what do you think are the 2 different genotypes that can give you the type B phenotype? Exactly. So you could be this, or, sorry, or, no, I'm doing the right thing. Just thinking out a little second. Or that. Alright, I'm going to move this type O down. We'll leave the band out of it, type O negative. What's the fourth blood type that I didn't write down? AB. Alright. So what do you think you need to be type AB? You need a G. Yes, exactly. You need a gene to make the A proteins. Oh, sorry, a version of the gene to make the A protein. You need a version of the gene to make the B proteins. That's type AB. So, what do we need to be type O? Yeah, you're right. That's the fancy H word for it. There's another way to say it, though. Go. Anyway, you got it. There's this powerful. So, codominance. Both traits can be equally visible. There's no blending or diluting. This is the difference. When we had incomplete dominance, we had a red flower and we had a white flower, and we bred them together and we got some of those kind of washed out red. It was a pink, right? It looks sort of like blending or diluting. In codominance, you're not building a protein here. You have the A and you have the B. You don't build a protein on the surface that's like halfway like A and halfway like B. What do? You make A because you have the A gene, the A version of the gene, the A allele. And you make B because you have the B version, you have the B allele. You don't make something halfway between the two, you make both. Now those of you who are clever probably already spotted the inconsistencies in this, which deals with how closely you're looking at the cell of the protein. But we'll talk about that later. I don't want to confuse people. This is still the terminology that's used in genetics. We would agree that the AB blood has type A and type B. It doesn't have proteins that are in between the two, right? You understand that you can still have a recessive, one that's recessive to these two dominants. That's the I. Get Harris? Alright, so let's talk about pleiotropic, multigenic, and then environmental controls. It's good stuff. If we say that a gene is pleiotropic, that means it controls more than one trait. So pleiotropic, like the sickle cell or malarial resistance, controls more than one trait. Multigenic is where more than one gene controls a trait. We talked about human skin color. Do you guys remember that? Alright. So, and then the third one, environmental controls. That's like my favorite one. We'll talk about that. So pleiotropic genes are genes that control more than one trait. Another example would be the albinism pictures. But the thing that a lot of people don't talk about, albinism is also a pleiotropic thing. It doesn't just affect your skin or hair pigment, it affects light sensitivity in your eyes. If you're albino or even partially albino for one gene, you probably have eyes like strong sensitivity to light. Multigenic. A multigenic trait is where one gene controls, or where one trait is controlled by more than one gene. We talked about human skin color. But there's also animal fur color. We have a special word that's called epistasis. That's when gene A depends on gene B to make something. Remember we talked about metabolic pathways doing that. And in the mitochondria we had this enzyme makes something used by this enzyme and makes something used by this enzyme. And if you have a mutation in the middle one, you don't get the end result. If you have a mutation in the last one, you don't get the end result. You have a mutation in the first one, you don't get the end result because they're all interconnected. You remember that? Okay? That is called epistasis. And the example of that in the book is animal fur. It's a multi-step pathway that involves several genes to make the melanin have is pretty straightforward, okay? You've got BD or BB, what's the fancy H word for this? Homozygous dominant. Alright, here we have the other H, heterozygous, okay? So ordinarily, you get either one of these gives you a black mouse. And if you have little b, you're going to get a brown mouse. Does that make sense? Does that make sense? So, would you say black is dominant or recessive? Dominant. And how dominant? Completely dominant, fully dominant, because the heterozygous looks like the homozygous. Does that make sense? Alright? So the recessive is brown, the dominant is black, and that's the way it is. So if you have two copies of the dominant gene, you're going to be black. If you have one copy of the dominant gene, you're going to be black. Right? Unless that depends on some other gene. And it does. There's another gene, C, that comes further upstream. It makes what's needed by the B gene. If you have a mutation in C, you don't make any of it, so it doesn't matter what gene you have, and you're going to be a white mouse. Even if you have the gene that should cause you to be a black mouse, you have the gene that you have little b, and you should be a brown mouse, but you've messed up C, you're a white mouse. You have big B, you should be a black mouse. Doesn't matter, you mess up C, you're still a white mouse. Because C makes something needed by B. Good? That is epistasis. Epistasis is a word you need to know on the test. Okay, now we have the fun ones. Genes affected by the environment. You've already heard a little bit of this, but I'm cool with that. So, these are hydrangeas. They're flowers. They're pretty. Would you agree we got purple hydrangeas? Would you agree that we got blue hydrangeas? White, pink, red? How many alleles do you think we're dealing with here? One. These are all genetically identical. I cheated. I pulled this chart up the internet. Because now you can buy what happens is the color of a hydrangea depends on the chemicals in the dirt. Okay? Genetically identical, but if you put different chemicals in, you'll have different colors. And now, if you're growing hydrangeas, you can buy fertilizer to make those flowers pink, fertilizer to make those flowers red, or whatever. Back in the 60s, it wasn't that way. My grandpa was probably the smartest man I've ever met. He's passed away now. He didn't even have a high school education. He was an immigrant from Germany, came over with people without a middle school education. He's probably one of the reasons why I'm into science. He's always reading about science, always thinking, always experimenting. I should get pull that chart up there. That's all now well known to a lot of people. 60s it wasn't. Figured out by trial and error with some different chemicals. This garden, that's what it came from. Up in Winter Park. And his big claim to fame was that this is how he would get customers. Business A comes up to business B. Gosh, your flowers look really good. Who's doing your lawn? So-and-so. It's Albert Meyer. Let's talk to Albert Meyer. So they talked to him. And Albert Meyer would, that's why we built into Albert, by the way. Albert Meyer, he would say, now, how would you like side of it red, this side of it white, this side blue. Well, we'll plant another one just like on the other side too, so that way you'll have a red, white, blue, you know. Christmas. Then we'll make it all red and green, you know, the leaves, you know, red and green and white. We won't have any blues for Christmas. We'll just make it red and white with the green leaves. It'll look real nice at Christmassy. You'll be like, oh, you can do that. I can do that. And my dad used to help him custom mix fertilizers to change colors of hydrangea. The thing that affects the color, the pigment made in the hydrangea, is the chemicals in the soil, not the genes. Okay? That's the whole point I'm getting at. You don't need to tell grandma stories. That's the point I'm getting at. It's a cat. We're supposed to tall creature as far as cats go. What kind of cat? Oh, never mind. Where do Siamese cats come from? Siamese cat. See this area? This area? They have the exact same fur color genes. Exact same genes. There's not genes to make it black here and genes to make it whitish there. Genes to make it look like it's spilled coffee on it there. It's not like that. Don't do that. It is stained. What's happening? You have the exact same gene, but areas of the body that are cooler, taking the gene turns on. Areas of the body that are warmer, taking the gene turns on. Environmental control, again, environmental control of the expression of the gene. If you think about this, this makes sense. Those extremities might, I don't know why it's highlighted, but I know that what you're seeing, if you think about it, the coolest area of the body is the extremities, right? That's what turns black. Warm areas that turn white. It's not just cats. It is not just cats. I have never had the pleasure of doing this experiment. I so want to. In the bad old days when you could do cool things, we would have been allowed to, but now you can't. But I have been told that if you take Himalayan rabbits, shave them bald in a patch. And you let them grow their fur back, and you leave them alone, they grow their fur back. If you shave them bald and you make them wear an ice pack the whole time they're growing fur back, it grows back flat. Now, I am really, think about this. It could be a fundraiser. We could get rabbits, and we could get corporate sponsors and shape their logos into the size of the bunny rabbits, and then we ice them, and then we let the bunnies grow back, and then imagine a stampede of bunnies down the sidewalk like we watched earlier. They'll all say Publix on the side as they're running. Wouldn't that be great? How much do you think that Publix would pay for Publix on the side of the bunny rabbit? It would be great. And the great thing is after they molt 2 or 3 times, they're going to lose black, and you can sell the same rabbit slide, you can advertise it to another company. That'd be great. Or of course you could go and you kill the rabbit then and use its skin for whatever, and it says Publix, it's in the fur. It's awesome. And just in case you're wondering, it's in the PowerPoint. It tells you exactly what gene is involved and what temperatures you have to achieve and blah, 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 blah. Good? Yeah, we know this. I've just never been allowed to do it, and now Pete has messed with all of it. It's not fun to be biology for you. Good stuff. Anyway, are you down with this? Does this make sense? We talked about this one before in the other video. You remember the other video? What's important about that other video? It's on the test you're doing on Friday. Remember the sex determination video you saw in PAL? There's a video that I showed last week on Friday, but I put a link to it in PAL so you could watch it. And if you want, I'll even show it to you when everybody else is running off. It only takes, I think, 2.5 minutes, 3 minutes. But it's all the weird ways that sex is determined in animals. Because it's not just the way that we're familiar with the woman has 2 X's and the man has an X and a Y, and he gives either an X or Y, she always gives an X and her egg. Yeah, that works for mammals. Actually, most mammals. There's platypus, of course. saying. But the alligators do it this way. A lot of reptiles do it this way. Temperature controls sex. All right? If the temperatures are low, you're going to have boy alligators. If the temperatures in the nest are high, you're going to have girl alligators. That's not what genes say yet. That's what temperature they are when they hatch out. How's that for cool? You're not nodding. It's pretty cool. All right. So most of the traits that we have in humans are multigenic or polygenic, meaning skin color, running speed, blood pressure, body size. In reality, this clearly is not something that is a single gene trait, although a lot of people try to teach it that way. And I'm not going to lie to you guys and say it is. That's why I linked to this Myths of Human Genetics. I would totally recommend reading it. Basically what you'll find out is that what is taught in 80% of the classrooms in the world is wrong.
I remember them telling me that.
Yeah. Yeah.
High school, yay. All
right, so let's go back to Mendel got lucky. Every gene, he looked at 7 traits. They were all on one chromosome, right? That you didn't have 2 genes on the same chromosome. Each one had its own chromosome. When he looked at these traits, they were all complete dominance. There was no there's no incomplete dominance to deal with. And they all segregated real nicely. It was just a the truth is a lot more complicated than what Mendel thought it was. All right, here's our big fancy human skin color gene from the book. And as I said before, you have a whole lot of different variants. This is showing if you had just 6 different genes, yeah, and of course each person has one set from dad, one set from mom. With just 6 different, you would have this much variation in skin color. And we have even more than that. Would you agree? That's why they think there's even more genes involved. All right, so the take home here is that yes, your genotype matters. But the things that make your phenotype are not just your genotype. That's what they used to teach. In reality, there's the action of other genes that work together and even environmental influences. And all those things together determine your phenotype. Are we good? Yep. All right, so we got questions. A red carnation and a white carnation produce offspring that are all pink. The type of inheritance is incomplete dominance. All right, if an allele for tall plants is fully, not incomplete, fully dominant to short plants, what offspring would you expect from this cross? All tall. All right, fur color in rabbits shows incomplete dominance. Well, they even told you that. Okay, so if you have fur color black to fur color cream, and then you have fur color white, what is expected from a cross of a cream with a white? It's a 1-to-1 ratio. It has to be a 1-to-1 ratio. Remember I told you anytime you had a 1-to-1 ratio, it was one gene. We agree it's all one gene. It's gene F, right? One gene, one parent heterozygous, one that's homozygous something, right? There you go. And that would be the opposite of the problem that we worked earlier. Well, I erased it, but the one right there, where I did it using complete dominance. Here you get your 1-to-1 ratio with incomplete dominance, or 2-to-2, 1-to-1. Does that make sense?